Professor Kerry Sieh, Professor Chen, ladies and gentlemen, good morning. Okay, I'm Dean of College of Science. I would like to express my sincere welcome to Professor Kerry Sieh. He is able to deliver a lecture here. Okay, and this is a part of the lecture series. Actually, it's a number 3 lecture, so-called the 大师讲座 lecture series. Okay, so it's really our pleasure and honor to have Kerry here to deliver a lecture. Also, it's my great honor to host this lecture by the invitation of Professor Chen. I will just give you a brief introduction about Professor Sieh. He's a world-renowned geologist, studying the cause and the pattern of great earthquakes. He initiated the field of paleoseismology when he was a PhD student in Stanford University. I think that's a very important remark in his life. Back to the 1970s. He is the first person discovering the pattern of great earthquakes generated by the San Andreas Fault in California. So inspired a tremendous amount of earthquake research in the last 30 to 40 years. So after he received his PhD in Stanford, he moved to Caltech to continue his research on paleo-earthquakes and active faults at many different places around the world. During 70s to 80s, Dr. Sieh not only conducted numerous fault-specific studies to understand the pattern of great earthquakes, he is also actively applying his research to heather vegetation and becoming an early participant in several key initiatives, including the working group on California earthquake probability and the Southern California Earthquake Center. His footprint not only covered the San Andreas Fault and other active faults beneath the Great Los Angeles area. He also advanced in knowledge on the neurotectonics of other major plate boundary faults, including the active faults in southern China, Sumatra, and also Taiwan. Because of his excellent research, he was elected as a Fellow of Geological Society in America in 1996 and became as a member of National Academy of Sciences in the United States in 1999. Since the 90s, Kerry and his colleague conducted to push frontier earthquake geological research to a new dimension, combining with the growth record of coral and the high precision uranium-thorium technique to understand the patterns of great earthquake from the subduction zone. Excuse me. While his research offshore Sumatra led to the installation of Sumatran GPS array right before the recent giant earthquake. So that's a very important achievement. The network later became invaluable to the study of subduction zone earthquake and reforming our understanding of megastrate earthquakes. In 2009, he just left from the Caltech and established the Earth Observatory of Singapore to conduct a series of nature heather research in Asia. So from the United States to the Asia area, he received the Henry Fielding Medal from the Geological Society of America 2013 and elected as the Fellow of American Association for the Advancement of Science in 2017, last year. That's because of his outstanding contribution to the seismology and the natural hazard research. So throughout his career, he constantly developed new ideas and the techniques that placed him at the forefront of understanding the story hidden underground and actively bridging these new scientific discoveries to other researchers to understand the potential impact to our human society. So Professor Kerry Sieh's achievement is to a lot of influence to our human society. So we hope Professor Kerry Sieh's presentation today will inspire all our audience, particularly for the young generation and the students, and really hope to help them to develop those young students for a successful career in the future. So please join me to welcome Professor Kerry Sieh.
谢谢您，刘教授. That's the extent of my Chinese, I think. It's great that we have a fairly small audience today, and I would like us, if we can, to do what I was used to at Caltech, and that is, in the course of my talking, please feel free to raise your hand and ask a question at the time you don't understand something, rather than waiting until the end. I think it could make it much more interactive than if you just listen to me. Now, I know, having worked now in Asia for almost 30 years, that you won't do what I just asked, right? Because you're too respectful to ask a question, but I think it would be more fun if we could do it that way. So please feel free to interrupt. Also, I understand from Professor Chen that we have about 2 hours together, so my talk will not last 2 hours. So if you interrupt, it won't mean that I can't finish, okay? I'm going to talk about two things today that are only related by the fact that they're geographically close. I was working on a problem in Southern Laos on an impact of a meteorite, and a dam failure happened in the course of just the last couple of months in that exact area. So I'm going to combine the two. And I think what I'll do is, since we have a long time today, I thought I would just stop maybe at the end of the first part, give us maybe a 5 or 10 minute rest or a question period or whatever, and then proceed to talk about the other one, okay? Let me just say also, thank you very much for that wonderful introduction. You've done a lot of homework. I've forgotten about many of those things. But let me just say, especially to those of you who are still students, that what's always motivated me is not the honors that one might receive upon doing something judged to be important. I've always just been excited about the dynamic planet I live on. And you know, as a kid, I used to play in the woods and hurt my friends accidentally, and you know, and stub my toe and discover something under a rock. And I think that just led to an innate curiosity about how the world works. And by chance, I happened into earthquakes, and I happened a little bit into volcanoes, and I happened a little bit now into meteorites. And you know, we Earth scientists are blessed, I think, in that we look at the emerging properties of the Earth, and we get excited about an earthquake, or we get excited about a volcano, or we get excited about a meteorite impact. And what more can you ask for in life than to be passionate about something that interests you, huh? So let's take a look at a couple of things that have interested me lately. And I'll start by saying that let me actually say one other thing too about NTU Taiwan. This place has a special place in my heart. I first started being interested in Taiwan, I think it was the exact same week that Bruce Hsu started as a graduate student at Caltech. Wasn't it the first week you were there? September 1999, right?
In July.
Okay, he'd been there a couple of months, and I don't think he was going to study earthquakes. But anyway, the Chi Chi earthquake happened in September 21st, as you know. And I said, Bruce, and one of my colleagues said, let's go and let's map this big earthquake rupture, because that kind of rupture doesn't happen very often. And I says, oh gosh, I'm awfully busy. And, but he dragged me over here, and in preparation for that, I asked this new graduate student who I didn't really know, Bruce, you know, who should we work with in Taiwan? And he listed 4 people, including Professor Chen and 3 others, and thus my involvement in Taiwanese geology began, thanks to Bruce and Yu Gao. And then I was here for a sabbatical in 2003 for 3 months, and I got to know the campus a bit. So, and now 2 of my students have come back to NTU as professors, Wang Yu and Bruce, and so I feel a particular affinity for this place. I was taking a holiday soon after, a year or 2 after I arrived in Singapore, taking a holiday in Saigon. And I was walking along, and you know, Saigon looks like every other major city these days. It has all the big global brands, the Gucci's and the Versace's and all this sort of thing. And I thought, how boring, it's like every place else in the world. But I came across a little jewelry shop, and I walked into the jewelry shop, and I've always been intrigued by these little sparkly things, and I never want to pay for one. They're so small and so expensive, but I thought rubies and sapphires and spinels and so on. And then on the back of the wall, I saw these little black poops. And I thought, what on earth are these? And I asked the lady there, and she says, oh, those are Tektites. And I said, really, what's a Tektite? And she handed me an abstract, a scientific abstract that must have been photocopied 50 times that I could barely read. And it explained that these lie all over the place in Southeast Asia. And in fact, they're seen throughout this entire area with the, could we turn, yeah, great, this entire trilobate, you know, bird's foot sort of pattern. And I thought, well, that's interesting. I'd never heard about these before. And I became totally absorbed in these guys and started thinking, well, where's the crater? Where's the hole in the ground that the meteorite hit that spewed out all of this stuff? And she said, well, the literature says nobody knows. People have been looking for 50 or 100 years, and nobody's found the hole in the ground. And yet the volume of this stuff indicates that it should be 15 kilometers in diameter, maybe even 200 kilometers in diameter. And I thought, what's wrong with these people? Why can't they find this? It must be very obvious. And if it's 15 to 200 kilometers in diameter, it's got to be a hole somewhere. And then I realized it was all geochemists who are working on this problem. And geochemists don't tend to do much field work, and they don't tend to look at landscapes and so on. So I thought, well, maybe it's just because they're petrologists and geochemists, and they spend all their time looking at these Tektites. So this just shows you a bit about the Tektites, so the different kinds. This is a typical one that what it looks like when they land in Australia. So this is about a centimeter across, and you can see it's spherical, but then there's a little ring around it. So that indicates that it melted when the impact occurred. It went flying up in the air very, very rapidly up into space, and then it came back down, and it came back down and it congealed in space as a sphere. It came back down, and as it re-entered the Earth, it came in so fast it started to remelt again on the leading edge. And so it formed this flat. What happened here? All right, so it's sequencing through, telling me that I have to go faster. All right, I don't think so. All right, so this guy basically is flanged, or what they call aeroablated, all right, and remelted upon entry. So it went way up and it came way down, and it landed, I don't know, 8,000 kilometers away. So it had to go out awfully fast, kilometers per second, and land very fast back in the atmosphere to melt like this. These guys are microtektites, and you find them all over in oceanic cores. The ODP cores often will have tektites in them. All the places you see here with these dots in the ocean are places where microtektites have been found in the ocean. These are less than a millimeter typically, but beautiful little things. You could wear them around your neck and nobody would see them. All right, and then over here, these are more like the ones that we borrowed from one of the geoscience at Tsinghua Lo's desk today. And these are dumbbell shaped, they're plate shaped, and the dumbbell is actually formed by the molten material flying up in the air and spinning like this, and so it ended up accumulating material on the tips. The plates or discs formed by, they're flying up in there like this, and they're spinning like this, and they become ablated, they become flatter, all right? But they don't, when they come back down, they're coming down slowly enough that they don't remelt. And they typically are found in this area. And then over in this area, shown with this strange little yellow pattern I drew, these are ones that are called Muang Nong type tektites. They're named after a little village in central Laos, very close to the Vietnam border. And this is one that I collected just a year or two ago, and it's 25 centimeters in diameter. And it's about 200 kilometers from where we think it came out of the ground. So imagine if this happened at night. I hope it happened at nighttime. Imagine what it would have looked like. All this stuff coming, raining up out of space, flying down, hundreds and thousands and millions of these coming at you all at once. It must have been quite a sound, and it must have been quite a blaze of shooting stars all coming down at the same time. Hopefully it happened at night, so it was exciting in that regard. All right, so we also know that these actually were hotter. They were melted, they were hotter, they have less water vapor in them, and so on. And these are actually cooler. So you go from hotter to cooler, you go from smaller to bigger, and so everybody thinks that the source is somewhere up in here. Now, to be fair, one of the reasons that nobody discovered the crater is that people started working on this in the 1960s in a serious way during the lunar explorations. And here's a crater on the moon, for example. The reason this crater hasn't been found over here could be that because of the instability politically in those days. And it was difficult for geologists to work in Laos or to work in Vietnam or to work in Cambodia because of the way Americans screwed things up there during the 60s and the 70s and 80s, okay? And there are still problems with dangers in the field with landmines and RPGs and unexploded ordnance. But basically, the geochemists weren't that smart. All right, so where is it? The geochemists and petrologists are smart enough that they were able to figure out from the chemistry and from relic minerals in the grains from tektites and microtectites here that in fact the target rock was primarily a very fine-grained sandstone, probably of Mesozoic age. Why is it doing this to me? Let's see, where am I going here? All right, is that where I want to be? Let's see here. All right, so fine-grained quartz sandstone, very high silica contents in these. Sometimes the silica is up to 85% or so, more commonly 75 to 65 or so. A broad range of silica contents clearly shows that the rock was heterogeneous, but in fact primarily a fine-grained quartz sandstone. Now, the crater has to be tens of kilometers in diameter based upon the volumes, based upon the iridium anomaly associated with it in the sea. And everyone agrees that it has to be within this region where these Muang Nong tektites are found. So Muang Nong is about right here. And these big black dots show where tektites are found that are bigger than a kilogram. And the littler green dots are where they're less than a kilogram, all right? And some of these are in situ, very few are in situ. Most of them were collected without being in situ, so we're not quite sure exactly where they came from. But somewhere in this region, it's believed that the impact has to be, and yet no one's found a crater in this region. The most likely place to find for a meteorite to hit fine-grained quartz sandstone is in this dark gray area, the area called the Curette Plateau, a fairly flat region of Mesozoic interior drained fluvial sandstones, mudstones, evaporating deposits, and so on. And so we started thinking, well, it's likely to be somewhere in here, given the chemistry, and it's got to be within the Muang Nong region. So let's start looking. A crater here this is almost flat topography, so a crater there would have to be visible unless it had been eroded away or unless it had been buried. Now, I haven't mentioned the age yet, but the impact occurred about 790,000 years ago, so it's quite some time ago, but it's still late Quaternary, so it's not all that old. And so the question is, could you have enough erosion to erode a crater that probably has a rim of, say, 250 meters in height above the landscape? Could you erode that away and not be able to see it? Lots of people have looked. There are lots of domal anticlines and quark-reversal dipping synclines, partly related to the evaporites underneath, and nobody's been able to find the crater. Now, if you look carefully at the Curette Plateau, shown here, there are lots of places, we've only shown a few here in this figure, but there are lots of places where you can see these little guys sitting on the surface or within a thin little deposit, flat-lying deposit, only say 10, 20, 30 meters or so above the current rivers. So in the last million years or so, the amount of incision in this area has only been a couple of tens of meters. So there's no way you could erode away a 100 or 200 meter high crater rim. So erosion's out of the question. We even have basalts over here. Let's see, where is it? Here we go, this guy. These guys are basalts that have ages of 1.1 million years, and they're within 50 to 30 meters of the present-day Mekong River. So no way could you have eroded this thing away. So burial is really the only option. If you want to bury a crater, if you want to have a crater in this region, you have to bury it. Yes?
Sorry, I have a question. So,
sure.
Now you look for Tektites to catch the crater location, right? So I'm wondering if you check another kind of untitled mineral about high pressure mineral, because the
Yep.
high
Yeah.
right.
Right. Right. So one thing we want to look at that I'll show in one of the very last slides is quartz actually can be shocked by these impacts, and you can have these planar deformation features, or PDFs or PFs, that indicate 10 gigapascals, 20, 30, 40, 50, 60 gigapascals. So I'll show one slide of that at the end. This, of the 5 tests I have for where thinking we found the impact site, that's one of the tests. Okay. Good for you. Thank you for making this interesting. All right. So we think in looking at this general map, the only place where there's a big deposit that's thick enough to bury a big impact crater is right here. All these red features right here are all lavas. They're all mostly basaltic lavas, and they're Cenozoic in age, Neogene in age. Nobody's really done much to say much about these or to characterize them very much. I'm not sure why this is doing this. There's a little gnome around here that wants me to make sure I finish this. So within this area of gray, this is our best candidate for where the crater could be buried. So let's take a look at that. We think, in fact, that's where the crater is, and that it's almost totally buried. So here's the Mekong River. It's about 1 kilometer wide for scale. Here's a scale bar. And this plateau is called the Bolivan Plateau, and it rises, these cliffs are about 1 kilometer high. I wonder why it's doing that.
Happy Halloween.
What's that?
Happy Halloween.
It's All Saints Day. You're supposed to be good today, right?
Right.
Halloween was last night. All right, so anyway, we'll just go faster here. Anyway, this is a 1 kilometer high plateau. It basically has an erosion surface on it, on the old Mesozoic quartz sandstone. And you can see here from the contours, these 50-meter contours, there's a big dome here. And it moves in this direction, big fans here, a big fan here, a big fan there, right? And those are not alluvial fans. There's no source of alluvium up here. This is all a volcanic field. So this is the summit region of the volcanic field. It's about 100 kilometers from there to there. The volcanic field goes from here down through here, covers this area. Whoops. All right, I'm sure, Wang, you could figure out how to solve this problem, but I think we'll just go ahead with it. All this is volcanic debris. It's all basaltic lava, as it turns out, tholeiitic and alkalic. So that volcanic field rises about 350 meters above this former erosional unconformity on the Mesozoic sandstones. So here's a very simplified geological map. We made this map basically from SRTM 30-meter topo, and basically, don't pay much attention to the colors here, but basically they're all basaltic lavas. The lighter colors indicate younger ages based upon soil development, and we now know from the actual ages. In here we could actually hide a crater about 15 kilometers in diameter underneath this 350-meter thick layer of basalt. And here's where all these little pink guys are cinder cones or sources of the lavas. So there's a big source of lavas hundreds of little events throughout here, and the volume is enough that it's actually spilled down through here, spilled down through here, here, and down through there. All right, so that's a hypothesis. Now the question is, how can we test that hypothesis? I'd never get away with sending in a paper for publication if I didn't prove it beyond a reasonable doubt. So let's do 5 tests in the next few minutes. Is there first of all, if the lava started being there before the impact happened, then there should be basaltic lava mixed in with the quartz sandstones in the tektites, right? So this meteorite comes in, probably a couple kilometers in diameter, comes in at 30 kilometers per second, compresses the sandstone and the basalt to 25% of its original volume, okay? There's a rarefaction wave that causes that causes melt, causes it to form a plasma. That comes out, it vaporizes, then it congeals again into the tektites, and they go flying out to Australia, flying out to Singapore, flying out. I think you don't have any here, except for the ones that your professors have brought back. So there should be some basalt in the chemistry if, in fact, the field had started forming before 790,000 years ago. Oops, that's not right. Okay, and if there is basalt in the tektites, can we show by dating that they were there before the impact? Are the basalts covering the proposed impact site younger than the impact? So do we have ones that are older that could be incorporated into the tektites? Do we have ones that are younger that totally buried the crater? That might be the most interesting test, the most definitive test. If we find out that the lavas on top of where we think that impact is are older, then even a Geology 1 student knows by the law of superposition that younger stuff buries older stuff doesn't bury younger stuff, right? All right. Fourthly, is there a gravity anomaly associated with the impact site? The impact's going to basically compress material. It's going to basically throw a bunch of stuff up that falls back in that's looser than the original sandstones. Is there a hole in the ground filled by basalt, in which case there might be a positive gravity anomaly? So is there a gravity anomaly? If there's not, then it's going to be special pleading to say that there's a crater there. And then finally, is there any evidence, getting to your question in the back, is there any evidence of proximal ejecta near the proposed site? And in that proximal ejecta, is there any shocked quartz, any indication of high pressures? All right, well, let's test the first. Test number 1, is there a basaltic component in the tektites chemistry? We took just published data, 300 or so samples that have been analyzed over the years, and then did a principal component analysis, and using just the first 2 principal components, 50% plus 23%, about 73% of the differences in the chemistry. This is potassium, magnesium, calcium, silica, and a few others. You see a tremendous range in the chemistry, and they're right between a tholeiitic basalt and the sandstones that we've analyzed. So it looks like we have a basaltic component in the tektites. Now that's been inferred before, but nobody actually then said, well, where could that be geographically? So the chemists recognized this, but they didn't look at it as carefully as we have. Thank you. The older you get, the less you see. All right. So just drawing a ellipse around the majority of the Muang type, the nearby tektites, okay, and a blue ellipse around the Australites, the ones that are found in Australia, you can see that there's a difference in the center of mass, if you will, of where these fall. These guys are closer toward the basalt field, and these guys are closer to the sandstone field. So it looks like the stuff that came out and came out more slowly, it was cooler, probably a little further away from the actual impact site. They actually seem to have more sandstone in them than the ones that came out faster and flew further away. So it looks like we might be looking at some stratigraphy here. It might be that the basalts were preferentially taken further than the sandstones. But notice that even among these butterscotch-colored Muang types, there's quite a range, all right? So probably, even if there was a very nice stratigraphy at the site, it probably got really pretty badly mixed up in the course of this 30 km/s impact. All right. So if one looks, there's another, let's see, there's also an extraordinary amount of beryllium-10. Now, do any of you know how beryllium-10 forms on Earth? How about any of the students? Do you guys know? Okay, beryllium-10 is radioactive, and it forms by the spallation of oxygen and nitrogen in the atmosphere. Okay, so splitting it apart in the high atmosphere. And then it actually is rained out, and it basically is rained out, and it's incorporated onto hydroxides and other clay minerals in superficial deposits. So typically you have beryllium-10 sitting within a few meters or 10 meters or so of the surface as part of the weathering process. So it's strange, and chemists have known this for 30 years, that in fact there's an extraordinary amount of beryllium-10 in tektites, and yet the impact should have actually evacuated material from, say, 100 meters, 200 meters, 300 meters down. There shouldn't have been much beryllium-10, but geochemists have long known there's a lot of beryllium-10, and it turns out, so it turns out that this is another argument that the tektites, that the impactor actually hit basalt. A whole bunch of layers of basalt. So imagine if you had, say, 2 or 3 million years of basalt flows, one on top of the other. It's tropical, lots of weathering. Lots of weathering. This is a 200,000-year-old basalt flow, and all that's left are these core stones. This is what we end up dating, but all the rest of it is just clay. All right, so you guys know that very well around here, that you want to try to help me with this? Okay, I'm technically incompetent. Within 100 or 200,000 years, most of the basalts are, I would say, 50 to 80% weathered to hydroxides and oxides and so on and so forth, in the process of making aluminum ore, right? In the process of making tropical soil. So this is a terrific place to store water, for water to bring in beryllium-10 and have the beryllium-10 deposit. So if you have one 5 or 10 meter flow after another over the course of a few million years, and each layer is weathered while it's, after it's been deposited, you could store a lot of beryllium-10 that way. Much more than you could store in the old Mesozoic sandstones, right? So the existence of beryllium-10 might very well indicate that in fact we impacted layered basalt, that it had weathered quite a bit. Now, it turns out that, remember I was saying that the distal tektites have more basalt in them than the proximal ones. It turns out that the distal tektites also have higher concentrations of beryllium-10. Ho ho. So put those two together, that's another argument that in fact that the layered basalts, the weathered layered basalts, were preferentially evacuated out to Australia, and these nearer ones had less of that superficial weathered material in it. Now here's a little model we put together, and ignore this part over here, but when you look at the amount of beryllium-10, the atoms per million grams, in the basalts, in the modern basalt, you typically see 150 to 400, and in sandstone, you typically see 0, okay, in bedrock. So what we're thinking is, now it won't advance when I want it to. We'll leave it there. Okay, so here's one of the arrow-ablated Australites. They come out like this, and they go out and they land all the way in Australia. The trajectory here is primarily through basalt, some sandstone, but primarily basalt. So these guys should have high amounts of beryllium-10. The big guys, the Muang-Nong tektites, if they come out on a trajectory like this, they're coming primarily through sandstone and a little bit of basalt, and so they're going to have a lower concentration. So these typically have like 60 grams per million, 60 atoms per million grams. These typically have 200 or so. And so this might explain, this different trajectories through different materials might very well explain why in fact we have these differences. So those two things then help explain why we have different chemistry, All right, now I actually want to advance it. So test 1 looks really interesting. It looks like there is in fact basalt in the and it's weathered basalt in the Tektites. Test 2 were the basalts there before the impact. We have 37 argon ages, and they are, here's the key for the ages. All these little dots here are dates, and you can see that there are quite a few that are yellow. Those are just older than the Tektites to about 3 million years. Dot, 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 over here, 7, 8 million years here, 1 million years here, and so on. And we have some that are actually even older. Okay, 3 to 16 million here and down there. So there are basalts that are older than Tektites in every single quadrant around the plateau. So that suggests that in the middle, at the crest, there probably was already a source flowing down to the north, to the west, to the east, and to the south. So it's quite plausible that, in fact, you gonna switch them? Oh. Wang Yu commonly saves me. Thank you. So from that test 2, we now know we do have dates that are older than the 790,000 year age of the impact. So it's plausible that there's material down there at depth at the site of the 15-kilometer crater that in fact was incorporated in the Tektites. So those first 2 tests seem to work. Is that enough? Would you guys be satisfied with just that? You gotta be satisfied with just that. You guys? You would? That'd be enough? What about my other 3 tests? I've got 3 more tests, okay? Okay, one reviewer of this paper says, extraordinary claims require extraordinary evidence. So we're trying to be extraordinary here. Thank you, Wang Yu. All right, so we have stuff that's older. So we've pretty much shown now that we have basalt in the source, in the Tektites, and at the proposed site. So now let's take a look. Let's take a look now at a little closer in this region where we think the impact occurred. I have 2 ellipses here. I'll show you later. This is actually supposed to be a circle, but in fact the screen compressed it east to west. So that's supposed to be a circle. This is supposed to be an ellipse about 17 by 13 kilometers. This is supposed to be a circle 15 kilometers in diameter. So here again are the flows in purple. And here are the sources. Here are the little cinder cones and little sources of the flows. And every single age within this limit and extending beyond it to some degree, every single one of these is younger than 700,000. Every single one. There's not a single one that's older. And if there had been a single one that's older, the whole hypothesis would be dead, right? So I think that's pretty brave of us to try to disprove the idea, but turns out everything turns out to be younger. And in fact, here are a couple, one right here and one right here, that are 790 plus or minus about 30,000. So they could be either older or younger. Okay. This one is actually overlying one that's 1.2 million, about 55 meters lower. So this guy probably came from a source somewhere up in here and then was buried by this blue one. All right, so the closest one we have to being older than the impact is way over here. And this is from a little mound that we originally thought was a flow or a source, but it could actually be a clast. It could actually be about a 200 meter diameter clast that was thrown out of the ground. Or it could be a flow that was simply a source that was flowed around by younger flows. So there's test 3. So now we have both younger and we have older. We have basalt in the Tektites, and we have younger ones, and they could totally bury a crater here that's 15 kilometers or so in diameter. All right, now let's take a look now at this guy. We're going to now do some modeling. I'll go through it very quickly to show that we could fit a crater right about in here using the gravity data. Now, this is a fairly complicated story. We collected over 400 data points, all shown here with the little gray dots, and those are all gravity measurements. And after taking out a regional gradient, and after taking out when you do a Bouguer gravity map, you have to subtract out everything above sea level, and you assume a certain density. Well, the density you assume is 2.7 grams per cc, typical continental crust. But what we have here is we have some basalt. So we had to take out the basalt too. So we had to make a structure contour map from the geological map, take out the basalt, and then we also took out some other materials. We end up with a residual then that looks like this. And right about in here is where that little ellipse would appear. So there is a beautiful, fairly large negative gravity anomaly, which is what you normally have with an impact crater because of all the shattered material and lower density crater fill. If we put in a 100-meter thick lens of lighter density material, 1.8 grams per cc, we end up with that. So we can get rid of most of the southern part of that anomaly by putting in a crater. Now, what the heck this is, we don't know. It's too far out to, if the crater extended to here, we'd probably see pieces of the ejecta blanket out here. So we're not quite sure what that is. But my point here is not that we have a beautiful, beautiful fit with a crater fill, but that we could hide a crater under here and we'd see it, and part of this anomaly could be due to that impact crater. So this test basically doesn't prove a crater, but if we didn't have an anomaly, something like this, if it were just smooth across this region, we'd probably have to say, that's a tough one. We should have had an anomaly and there isn't one, so what's wrong with our hypothesis? So test 4 basically lets us proceed, lets us continue. We can't say no, there can't be a crater. All right, test 5. Yes, sir?
Since all the ejecta goes to the south, then you must expect this is a pretty strong oblique heading, the outline
Yeah.
impact of the Earth. So wouldn't it explain some of the geometry of that gravity anomaly?
Yeah, why it's elliptical? Yeah, it could be. Now, it turns out that even if you come in at an angle as low as, say, 10 degrees of incidence, you still end up with a circular crater. This is what we've shown from, what people have shown from actual experiments. You know, you take an artillery shell and you fire it into some clay or something. You get, even as low as 6 degrees, you still end up with an almost circular crater. But when you get below that, you can end up with elliptical craters with a ratio of major to minor axis of about 1.4. So it could be that this came in at an extremely low angle, lower than 6 degrees, and in fact, it is that orientation. And in fact, the reason we picked this northwest-southeast orientation is because of the pattern of the Tektites all the way down to Australia, right? Yeah, we could. The only problem is getting one as big as having it include something down here. Now, it may be that when this gets drilled, we'll find that it's actually even bigger than we thought, and for some reason there was no debris out here because it came in from the northwest and almost all the debris is sitting out in the south. So that it could be it's bigger than we think. The ultimate test will be drilling it, won't it? All right, so 5th test then. Is there any evidence of a proximal ejecta near the site? And the answer to that is yes, right here. So of all this region in here, there are only 3 places where we think we see the possibility of stuff that got thrown out other than tektites nearby. One is up here, on these 2 little green dots, these 2 little green dots. These are actually enormous slabs of Mesozoic sandstone that are sitting on the ground, not connected to the bedrock. They're just sitting as enormous boulders, some of them 20 meters long, 20 meters wide. And these look like normal faults, turns out. So we think this is probably the edge, the northeastern edge of the crater, and this is probably debris that got thrown up onto the edge, and we think this is the same thing here. But most importantly, right here, we have a little bit of an area that is not covered by lavas. And this is very strange terrain. It's rilled terrain, very closely spaced ridges and swales, small little streams, hardly have any water in them at all. And right here we have by the way, this is jungle. This is hard to get through. I think you probably still have places in Taiwan like this, except that the typhoons keep wiping out the trees, right? But here there's no typhoons, and parts of this are absolutely impenetrable. So the only place we could find an outcrop is right there. And we drove right by it at first, not paying much attention to it, and I'll bet you would too, right? It doesn't look particularly interesting, does it? It's just some kind of layering here. There's some stuff in here and some stuff in here and some stuff on top. Let's look at it a little more carefully. When we came back down the road again a few hours later, wait a second, this looks interesting. When you make a detailed map of this outcrop, all these guys in pink here are boulders of fine-grained Mesozoic sandstone. And here's a scale. So there's some of them are big. When you look in detail here, what you see is that these boulders and cobbles form domains. So this actually was a boulder that's now totally shattered. It's not weathered. We see lots of places where we have weathered sandstone on this plateau, and nowhere does it look like this. Okay, it doesn't weather like this. Here's another boulder, and this is also totally shattered. Another boulder that shattered, another shattered, another one that shattered. That can't be a debris flow, right? You guys are, I'm sure you students have seen lots of debris flows in Taiwan. And you don't transport boulders together as families like this, right? You put them in the muddy flow, and they come down separately, and they land. And if you see an outcrop, I think I have a picture of Bruce standing on an outcrop of a debris flow deposit down near on the Mekong River, I think. Right? He was brave enough to climb up like 5 meters to be my scale bar, and they're all individual boulders. Okay, so these are puzzle pieces. So how could those have formed? Any ideas? Crashed. Yeah, it turns out these are 20 kilometers away from what we think the crater is, the center of the crater. If you eject this material at about 400 meters per second, it would land here at about 400 meters per second. So imagine coming in at 4 football fields per second, and coming in so dense that when you hit the ground, you can't explode into a jillion pieces and form a secondary crater. All these coming in basically within a fraction of a second together, shattering in place, and each one holding the other one in place so they couldn't then eject again. Okay? So this, I think, is to me, I'm 99% convinced that this is actually an impact breccia. It went out, and they came out, they broke into pieces, they came and they landed all at once all together. These green boulders and cobbles are mudstones, and they show the same pattern. They also came out. Now mudstone underlies the sandstone on the plateau. And if you read the meteorite literature, the impact literature, you'll see that typically the ejecta blanket has inverted stratigraphy. The stuff below comes out and lands after the stuff on top. Makes sense, right? You compress it, the stuff on top comes out, lands first, the stuff underneath comes out and lands later. So you typically invert the stratigraphy. All right, so now where's the basalt? Well, unfortunately, the road between here and the stream is about 10 meters. If there is basalt, it's hidden by bamboo and other brush that we couldn't cut through. So we need a backhoe to go out and find the basalt that should be beneath it. Anyway, so that to me is a pretty compelling piece of evidence as a geologist. Yes, sir.
Sorry. So you are mentioning that water are coming from the impact side, or there was in situ damage from the seismic wave?
Well, we don't see bedrock. This is definitely not a bedrock deposit. The bedrock is actually exposed about 10 meters below at the base of the streams. Right? So this is, and also the orientation of these boulders, the bedding in these, I should have shown the bedding. Actually, it's hard to show the bedding, they're pretty massive, but if you were to look at bedding, the bedding is all every which way. So it's clearly a conglomerate or a breccia. It's not in situ shattered bedrock. Now you could argue there's a thing called back venting. You may have noticed in a nuclear test, if you look at a video of a nuclear test, you'll often see a shock wave traveling over the ground, and when the shock wave hits a piece of ground, it actually, when the rarefaction part of the shock, first you have a compression wave, then a rarefaction wave. When the rarefaction hits, it actually causes an explosion of the ground. If the ground is saturated with water, or if it's just porous material, the expansion of as the rarefaction passes through, it causes an explosion upward of the ground surface. So you can explain that the back venting process if you see something fairly fine-grained. But if something as big as this, it'd be very difficult to explain. Also, that sort of process wouldn't, well, yeah, anyway, in any case, it's not bedrock. It's got orientations every which way. All right. So now the question is, so in come the impact experts, and they say, I don't think any of your 5 pieces of evidence are compelling. I'm going, really? And they go, yeah, if you can't find shocked quartz, then you haven't proven anything to me. So a lot of these guys who work on impacts elsewhere in the world and on the moon and so on, they say, unless you can find shocked quartz or shocked minerals, you haven't proven to me that you've got the crater. So we took a look at this boulder right here, and we took a sample out of there, and we looked at dozens and dozens and dozens of quartz grains, and here's an example of what we found. So we found shocked quartz, thank you very much. All right, so these are all quartz grains, here and here, and typically in a shocked system, you'll find maybe 2-3% of the grains will actually in thin section will display shocked quartz. So this is about what we see. We see 2 or 3%. So these right here are deformation features. We don't know whether they're actually fractures or whether they're or what they are, but they show up as these planar features, and so they qualify as PDFs or PFs, planar features or planar deformation features. So it looks like, so to many people who work in the meteorite business, this is the smoking gun. Now to me, this is simply auxiliary evidence. As a geologist, to me, I mean, the other 5 pieces of evidence were critical, except perhaps they were all 5 of the others were critical. But to some people, this is the most important part. Now, before we go on here, I'm almost at the end of this part of my talk. This layer here is an interesting one. This actually is what the Thai geologists have called catastrolus. Now, you all know what lus is, but they call this the catastrolus because they find it all over eastern Thailand. And in fact, it's what makes eastern Thailand a breadbasket for Thailand. The reason you can raise rice so well is because of this lovely, coarse-silled, very fine sand. So this is a wind-derived deposit, and we think, and they think, it's caused by one of 2 things. Either when the impact occurred and the temperatures went up to, say, 5,000 degrees centigrade, everything for hundreds of kilometers around was incinerated. You can imagine at 2,000 degrees centigrade, no tree is going to survive, right? It's just going to be incinerated instantaneously, all right? The shock waves blow things to smithereens, and then everything gets burnt and oxidized into CO2 and other things. So one possibility is that you made a barren landscape that would cover almost the entirety of the Curette Plateau, and in successive years, decades, centuries, before the jungle vegetation grew back, you had lots of winds that were simply blowing things around. So you ended up with this loess deposit, like you would, say, off the flanks of a big glacier, right? That's one hypothesis. Probably has some merit. Another hypothesis is that when the impact occurred, there was such an enormous amount of debris thrown up into the air, all the way into the stratosphere probably, that there was then a settling down of lots of fine-grained materials, and that formed the catastrolus. So either of the 2 hypotheses is possible. Anyway, that's just an aside. So basically, we've finished what I want to talk about with regard to the impact. I'm wondering if it's now been almost an hour. Do you all want to get up and just stretch your legs for 5 minutes? And then we'll talk about a dam failure? What do you think? Are you, I don't see anybody sleeping. Should I just go ahead, or, fellow in green?
Thank you. I just have a question about the evidence. Did you find, were you able to see any evidence of ore deposits around the impact? I mean, like metals or something?
So the question is there any evidence of ore deposits around the impact? No, we haven't. We have found some really interesting mineralogy within the basalts, though. Some of these basalts, the mineralogy, they're alkalic basalts and ortholeitic basalts, and I don't know the details of this. My colleague, who's the petrologist, knows it better than I do, but he claims that they come from two different depths, 85 kilometers and 65 kilometers or thereabouts. So down in the lower crust, or well, the upper mantle. And in some cases, we find these beautiful Well, rubies and sapphires come from this particular field in Southeast Asia, right? And in fact, one of my colleagues on this project is next week going to Cambodia to look at another one of these lava fields, these volcanic fields, to see if they can find rubies, all right, and zircons. We found a beautiful, beautiful xenoliths of peridotite. We found beautiful, beautiful xenocrysts there's some sanidine phenocrysts like this long that are purely clear color. I want to show Wang Yu, but I never got around to it, and because he likes minerals, he likes pretty minerals. So no, we haven't found any ore, but the fact is that most of the whole phenomenon is buried by young lavas. So only in those young lavas could you look for anything that would be economical. Fortunately, they found nothing economical in this region, or our deposits would be all gone, right? Yes, sir.
I can tell you if you have this kind of minerals in this basalt, that would be not like basalt.
Yeah, right.
Coming from deeper depths.
Yeah, yeah.
And another thing I want to ask is you mentioned that if there is a collision, and that will cause a fire because of high temperature.
Mm-hmm.
So you would find many kind of debris from trees or something like
Yes.
this. So you will have the charcoals.
Yep.
Have this kind of material around this area. So
Mm-hmm.
you can easily collect this kind of samples
Mm-hmm.
within the deposit and making the carbon 14 dating something like
Mm.
that. May or may not be. You use the other method.
Yeah. Yeah, so let me just repeat your question. So he's saying if there's incineration of the surrounding landscape, there should be lots of carbon for radiocarbon dating, right? And then also your comment about if you find things like sanidine, you're looking at alkali basalts. And in fact, that's correct. You know, the sanidine, of course, has lots of potassium in it. So there's a combination of alkali and tholeiitic basalts, and they aren't, one doesn't predate the other. These are both occurring, both erupting over the course of the last 16 million years. Very strange. So nobody really knows why those basalts are there. With regard to radiocarbon dating, radiocarbon basically has a half-life of only 5,700 years. So by the time you get to 50,000 years, it's dead. So this is more than an order of magnitude older than what we can do with radiocarbon. But some of these flows are within radiocarbon range. And we'd love to dig under some of the younger ones. One of them, I think, still has lava tubes that have collapsed that haven't been filled yet. So I'm guessing that the youngest ones are probably barely prehistoric. So those could be dated by radiocarbon. But we have to get out there and dig underneath them. And it's harder to do with basalts than it is with the sediments I'm used to working on with earthquakes. Right?
Yeah, another thing is concerning about the shape of Australia.
Mm.
You said you have a core. That was made of during the first melting stage. So we can understand that is because of injection. And the second part is the ring. And when the ejecta goes up to the high altitudes,
Mm-hmm.
so you it loses the speed. So how can you make another melting to the ring?
Actually, if you take it up into space, you no longer have friction, right? So once you get out into outside the atmosphere, you can continue at about the same speed, but then the Earth's gravitational field pulls it back in, right? So the vertical slows down, but the horizontal can keep on going. Bruce made this calculation for me one time for a volcanic class, and I used the same solving two equations to get the answer of the 400 meters per second. But when it comes back down again, when it comes into the atmosphere, if it's coming down fast, the frictional heating could actually cause melting of the leading edge, and that's the way that most people who've collected these australites explain them, that they come down fast enough that they actually have enough frictional heating to melt the leading edge. Does that answer your question?
Yes, but still hard to believe.
It's still what?
Hard to believe.
Hard to believe. Yeah, but you know what we geologists often say to geophysicists? We often say that if it has happened, it probably can happen. So these australites quite commonly, they're only this big or so and smaller, but they commonly have these flanges around them, so they kind of look like little mushrooms. Probably they did melt upon re-entry, and you don't see them actually closer to the source. So the closer to the source, they probably didn't have the same velocities upon re-entry. they became spherical. They became spherical or dumbbell-shaped or plate-shaped. So they're clearly streamlined. They're clearly aerodynamic, but they're not melted upon re-entry.
Okay, there's a minor question. Why you put in your early slides that you have a lot of localities for those tektites, but you also put on some localities saying that without tektite.
Mm-hmm.
What does it mean?
That's a good question. I think that if you look at the ejecta blanket around a crater on the moon, you see that there are places where there are ribs coming out. There's more debris coming out in sort of starburst pattern, and places in between with less debris. So I would assume that what that means is that they, that they didn't land everywhere. Now, a drill core is only going to be this big around, right? Now, if you look even in the proximal regions here, I'll show a slide during this second part of the talk. If you look at an outcrop, say only 50 kilometers away from where we think the crater is, you'll have a deposit of gravel, which we think is basically airfall, but not tektites. And within that deposit, you might find in a 10-meter exposure, you might find 2 tektites within that deposit. So clearly, they didn't form a uniform deposit like, say, an airfall from a volcanic eruption. So I think it would be expected that many of the ODP cores would not have tektites in them. You look very skeptical. Okay. All right. So should I go ahead with the dam failure? All right. So here's a beautiful exposure of one of the places we actually sampled lavas, and here we are 45 meters below a lava that's almost the same age as the impact. We sampled right down here. It was quite wet, and it turns out this is 1.2 million years old. So this waterfall is flowing over stuff that is maybe 1 million years going down to 1.2 million, and probably was there at the time of the impact. We'd love to have enough exposure to go between this 1.2 million guy and the one that's about the age of the tektites and see if we can find the ejecta blanket sandwiched in between the basalts. But there's a lot of greenery here. You guys in Taiwan are used to greenery, and you're used to it being difficult to get through it sometimes. All right, so you all probably know that the government of Lao PDR has as a major economic thrust the construction of dams across the Mekong and across some of its major tributaries. Here's a map that I just pulled off the internet that shows where some of those are and where some of those will be, or where they've been proposed. One's been canceled. The ones up in the green are actually in China, I think. So those are actually already operational, or in Myanmar. So lots of dams across the Mekong and actually across tributaries as well, and the tributaries don't show here. The place I've been talking about just now is right here where the blue star is. And one of the dams being built for the reason, of course, for the dams is hydropower. And these are politically very controversial, as you know. And people who live locally and make a living on the landscape, they have complained about flooding of villages, flooding of forests, flooding of fields, and so on. There's issues with regard to the ecology of the Mekong and its tributaries as well. So this is a very politically charged topic, and I've chosen in this audience to basically tell you what I think happened in this dam failure. I gave a talk in Korea a couple of days ago where I took out most of the good slides because a Korean company was building this dam, and I wanted to make sure I didn't get myself in trouble either with the Koreans or the Laotians. So anyway, so let's take a look now. So there's our proposed crater, as you know, and again, it's actually spherical in this slide. Okay, that's 15 kilometers in diameter, and this is where they've built a reservoir, and I'll show you some details about that. So the next slide is just the area of the reservoir. It's this eastern part of the plateau. Again, the cliff here is about 1,000 meters high. So erosional surface on Cretaceous sandstone here, and erosional surface here with a small amount of sediment from this tributary to the Mekong River. All right, so I drew this in actually before the dam was being, while the dam was being constructed. They started about 4 years ago. They finished construction back in about April of 2017. And here's a photograph off of the web showing the main dam. So the main dam, that corner is this corner. This corner with the spillway is this one. So the spillway is basically right above the old original drainage. Okay? So that spillway should maintain the level of the lake so that when the lake fills up, the lake can't fill up higher than the spillway unless it comes in some incredible torrent that raises it faster than the spillway can drain. That doesn't make much sense because basically this was a river before, and it was basically, and if the river spillway is about the same width as the river was, it should be able to handle the discharge from the entire basin. All right, so there's the main dam. There's a tunnel built, finished right here, almost horizontal tunnel, slightly sloping from here to here. And that tunnel connects the intake here in the reservoir, it's down below the top of the reservoir, with the penstocks over here, where the water comes out and runs down a race and generates electricity, right? So it turns a turbine. The turbine has a wire wrapped around it. The wire, you know, guys, physics 1, you know about induction. You generate electricity by spinning around a magnet. Right? So anyway, I should note that picture here. Here's a view of the cliff, part of the cliff, standing right about there, looking at this right here. Beautiful waterfalls over in here, very cliffy, very steep. And they're in the process back in late 2016 of finishing up this construction at the penstock and at where they're going to generate electricity. Now, we were a little bit surprised that the geologist told them to do put that major part of the facility here because this entire blue deposit is an enormous landslide. So here's a boulder with a 2-meter man for scale, or actually a 1.83 meter man, and there's one of the boulders of the landslide. So when I said this to the geologist, the engineering geologist in charge of the project, with his supervisor standing nearby, I said, "You know, you're putting this in the landslide." He goes, and he looked really embarrassed because he didn't realize it was a landslide. All right, so anyway, that's not where the failure occurred. So let's take a look now at saddle dams B, C, and D. So in order to make this reservoir high enough so that the intake would be underwater to supply water over to here, they had to put little saddle dams where the ridge line for the drainage basin goes down and then up, down and then up, down and then up. So they actually filled in with little earth-filled dams these saddles in the ridge so they could raise the water up an additional 20 or 25 meters or so. And it turns out that 20 or 25 meters, because the valleys go like this, amounted to about 2/3 of the total volume of the reservoir. So it was very important to build these saddle dams to make the reservoir big enough, high enough to get this tunnel to work. Okay? All right, so there's our situation. Now, let me go to a little movie. This now shows what actually happened between when the dam started filling about May of 2017 up until the failure. Whoops, I skipped it. Where to go? Hey, what happened? Okay, that's up until the failure. Why didn't it? I guess this just shows the filling. Okay, so there it's filled, and you can see there too that by the 17th of July, it had filled up to these saddle dams. Okay, so the saddle dams were just being utilized at this point. So the dam was basically pretty much full. Now, there's a comparison of before and after. So there's the last image I just showed you, saddle dam D, saddle dam C, D, E, and F, the main dam here, and here it is afterwards. So look at the difference in footprint. And notice also there's a little feature right here. That's where the flood occurred. So it's saddle dam D that broke. So the question is, why did saddle dam D break? So let's just take a look at some facts. I can't get in trouble for facts, right? So here's what it looked like downstream in the days after the flooding. Something like a couple hundred people drowned, and about, I think it was 10,000 or so people were displaced and still are displaced. The plateau is in the background here, so you can get an idea of the scale of that cliff. So the water came down from here and flooded this region. All right, so here's an image made from ALOS data. Wang Yu's wife, Nina Lin, made this figure. Anyway, this is an interferometric map that shows in the upper right what where the reservoir was full in red, what was left in black after the flood, and it also shows where the water came down. It shows part of the reservoir, where the water came down here. This shows areas that were flooded. Water came down here. Here's the cliff of the plateau, and this shows the big area that was flooded. The picture I showed you, I think, was from right in here, looking that way. All right. So there are hundreds and hundreds of, a couple thousand people who live in this area. This is that tributary. The penstock is over here. All right. So there's an image from space of the flood. Let's now take a look at the story. The owners claimed immediately thereafter, and are still claiming, that the failure was caused by an act of God. That it was caused, basically, this is a standard response when you would do when something happens that you don't want to be responsible for. So they're saying that it was caused by incredibly intense rainfall that basically caused the water to flow over Saddle Dam D and erode it. All right. Are you suspicious of that explanation without even knowing anything else? Yeah, I mean, usually in the tropics you get heavy rains, and you would think that heavy rains would be designed for, and so on and so forth. Well, let's not be suspicious yet. Let's just take a look at the information. So here's a record of rainfall as measured in some mysterious way by NASA, looking at from satellite imagery. I have no idea how that's done. Pardon me? It's trim data. And what is that, Wang Yu? I've forgotten.
It's a radar wave measure the particles.
Okay, in the rainfall? In the cloud? Okay, so it's some measurement of the water vapor when it's descending, all right. So it turns out that rainfall beginning when the dam was first filling in late May, there were rainfall events that were 20 millimeters per day. There was one here at 90 millimeters per day, so a pretty heavy rainstorm. And then this is the wet season. Here's the dry season for early 2018. This is when it's unbearably hot in this part of the world. And then rainfall begins again, and we're going through the rainy season up until just before the dam failure. So you can see that there were events that were on the order of 50 millimeters per day. So 5% of a meter, 5 centimeters in a day. All right. Now, if you do the cumulative rainfall with the green line, you can see that in the first season, basically the rainfall amounted to a total of on the order of 150 millimeter, 150 millimeters. All right? And the second year, leading up to the dam failure, oops, I should have said 0.2 here, right? Is that right? Yeah, it should be 0.2 rather than 2 meters. Okay. All right. So now if we look at satellite imagery, every place where there's a black dot, we have satellite imagery. And from that satellite imagery, we can tell what the elevation of the reservoir was by simply looking at the place where the water intersects SRTM 30-meter topo. Okay, so we can get a pretty good estimate. You make the measurements everywhere around for each particular image. You do an average, and you get a nice black square. All right. So we can see that the reservoir level on May 31st of 2017 was about 736 meters above sea level, and then it climbed through the season. So by the time the end of the rainy season last year, it was 764 meters. So the reservoir had filled by about 30 meters in that period. Then the dry season happened. And then early in the rainy season of 2018, we see a number of about 766 meters. And at the end, well, right before the dam failure, 10 days before failure, it was 769 meters. So we have a total of 3 meters of filling the reservoir during all the rain of the rainy season this year, all right? Including these relatively high rainfall days here. So 3 meters or so in the course of a few months with storms of this size or so. All right, now the reservoir elevation pre-collapse then was 769. Failure occurred on the 23rd of July. And here's the post-collapse elevation, about 747 meters. So something on the order of 20, 22 meters or so of drop in the elevation of the reservoir. Now, if you plot the volume, if you use those maps and the incremental elevations per image, you can actually get a figure that shows the actual volume that was lost during the flood. And it turns out that this much was lost just by going from 769 to 747. You end up losing well over 2/3 of the volume of the reservoir, which explains why they built Saddle Dam D. They needed more volume. All right, so that ends up being about 350 million cubic meters of water, much less than was initially estimated in the days following the disaster. So let's take a look now at the imagery of Saddle Dam D. Here's a fairly low resolution imagery of the dam. And let's look at a couple of points. 1, 2, 3, 4, these little green dots are the same as these. So here's the topographic profile with the vegetation removed. So we removed about 12 meters of SRTM elevation because trees in this area are about that high. So the dam top should have been about here at 800 meters or so, from here to here, and filling up this swale. The low point in the saddle is at about 769 meters, which is about the elevation the water had gotten to at 10 days before the failure. I would maintain that there's no way that any rainfall of any size could have filled up 30 meters worth and overtopped that dam in the course of the next 10 days. I think that's pretty obvious. Is it just a coincidence that the elevation of the base of the dam was reached in the 10 days prior to the failure, and that it probably filled up a little bit more before? Probably not. All right, so here's a photograph of the dam taken by I'm not sure who, but promoted by one of the major Korean television companies. And you can see there's a little crack right here. It looks like a little normal fault, a little slump of some kind. But you can see that there's a gravelly carapace, and inside of it, you can see there's some orange-brown material. So the middle of the dam is orange-brown material of some kind we'll look at in a second, and the outside is a carapace of coarse, cobbly debris or material. All right, here's another picture taken from the dam when a little bit more had happened. And for reasons I can't explain, the water level actually in the reservoir is actually probably within about a meter. I don't know, it's hard to say, but it's probably within, say, 4 or 5 meters of the top of the dam. Hard to see from this picture, isn't it? But it's higher than the base. It's higher than what we calculated, the 769. So there's something wrong with our analysis. But in any case, as the dam was in the process of beginning to fail, the water was within several meters of the top of the reservoir, but it was not overtopping it. So the dam is starting to slump. That's not supposed to happen, right? Okay, that does not look like act of God to me. It looks like, actually it's act of God doing something to an act of man. All right, so here we are afterwards, after the flood has happened. You can barely see down here, the base of the dam is actually a basalt flow. So the dam was built on basalt. This basalt is 16 million years old. We know from having dated it in a quarry nearby. And what do you see? Here's the dam undamaged. Here it is undamaged. And you see a big slump here, a big rotational slump. So for some reason, the dam was actually, the interior of the dam was no longer stable material, and it was slumping. And over here, the same thing. Big normal fault landslides, big rotational landslides. I will maintain that if that interior material was dry, it wouldn't have done that. But if it was saturated with water, it could slump. Okay? Notice there's slumps here as well, slumping into the canyon that was created by the evacuation of the reservoir. All right. Now, to make a long story, actually to get to the point, we think that what happened was that when they excavated the material for the quarry, from the quarries, they used local material to build the core of the dam, and then they used the basalt to make a carapace on top. And we think what they did was they didn't properly sieve the material to get rid of all the sand and silt, and they used a lot of silty material, a lot of sandy material that ended up being permeable. And so there was piping that occurred and saturation of the dam core, which caused the slumping, which caused the failure. So that's what I'm going to get to over the course of the next few minutes. Remember the deposit I talked about, the catastrolus, in that one outcrop before? There's the base of the catastrolus. This is all coarse silt and very fine sand, very sharp contact on top of this pebbly material here. That pebbly material is mostly laterite, but it's also got little bits of fine-grained sandstone in it, and where those two fingers of my distinguished colleague are pointing, those are tektites. And they're the only tektites we found in that entire 5-meter exposure, but it shows the tektites are only a small percentage of this deposit, which was probably the excavation of the sands and the laterites as the crater grew in the course of the seconds of its formation, all kinds of material that wasn't melted but shocked came flying out, and it landed like a volcanic airfall. And tektites came in and fell in with it in the upper part of the deposit. So a lot of the stuff sitting on top of the basalts in this area is this very coarse sand and gravel. They certainly wouldn't have used this, I assume. They would have not used gravel in the construction of the core of the dam. Here's one of the quarries near Saddle Dam D. This is the quarry that was used to make Saddle Dam E. And this unit here is part of this 5-meter high deposit here. Here's the basalt they were quarrying for the dam. That would have been underwater on the day before the dam break. All right, so there we go. All right, so here's a close-up. The catastrolus is basically the upper half of this deposit, and the lower part of the deposit is basically fairly loose river sands and gravels, and the tektites in between. All right, so we actually had an undergraduate do a little project on the catastrolus to see, in fact, whether it finds upward in one nice uniform way or whether it zigzags, as you'd expect if it were formed over hundreds and thousands of years. And it turns out that there's a sandy component here that finds upward by about 2 feet. That's probably and that's quartz. That's the original material that landed. And we can't really tell whether or not this came down as one event after the impact or whether it came in the weeks or months or years or centuries later. But then there's a finer component here that's actually clay, and that actually doesn't find upward, but it becomes more abundant upward. That actually is soil, and that's clay. So there's a lot of clay in this, and that's what they probably should have used for the dam. And my guess is they used this plus that, and therefore it was permeable. All right, so what do I say here? All right, so there you can see the black lava better that it's built on, and this is all processed material, I assume, but it's processed from what I just showed you. So my guess is they didn't process it properly. This is what I couldn't tell the TV station in Korea 2 days ago, that the investigative reporters found me somehow and wanted to ask my opinion, and I told them this off the record, and I told them where to go to look, but not to quote me, because I want to stay alive. This is a $1 billion project, so a little geologist's life is probably not worth all that much. All right, so let's take a look at things here, and I'm almost done at this point. So there's a permeable fractured lava flow. Many of the lavas that we see here have lava tubes. They're saprolitized, so they're sort of a loamy, sandy, clay carapace on top of them and filling cracks. Normally what you would do in making an earth-filled dam is you would excavate, you'd drill down, you'd excavate through that basalt, and you'd put in a very solid curtain of concrete or something else that would be absolutely impenetrable. Okay? Clearly they didn't do that here. So that's one thing, it seems to me, not being an engineer, a dam engineer, a civil engineer, I don't know if I'm right about this, but it seems to me that they missed that. They didn't do that, and they probably should have. The local clayey material that they use, I'll bet, is in fact clay, but I'll bet they cut corners and didn't just use the clay. They didn't take out the coarse silt and the sand, and so it was permeable. The carapace you can see there is of the crushed basalt, the 16-million-year-old basalt. And then here, let me just point out again, here are the slumps. So I think that basically the slumping wouldn't have happened if the dam materials hadn't been saturated. And the only reason they would be saturated is if they were permeable enough for the water on the reservoir side to penetrate through. And of course, the failure occurred soon after the base of the dam was reached by the reservoir. So it didn't take long for that water to seep through and to cause a slumping. Once the slumping occurred to a level where the water could flow over the dam, the top of the dam would be lower, so the water could flow over, and at that point it was a catastrophic failure. There we go. So that's it. So do you agree with me, or do you think, or would you be a consultant for the construction company and say that I'm totally off base? Now, a lot of us in young geology, in quaternary geology, whether we're working on faults or volcanoes or engineering of dams with the help of with civil engineers, a lot of us are motivated by the fact that we'd like the world to be a safer place. And we live on a dynamic planet, which has lots of challenges for us, and every day people die from geological hazards, and even towns disappear and cities disappear and so on. But we'd like to make the place, we're probably excited, humans are probably exciting because they live on an exciting planet. I mean, imagine how boring we'd be if we lived on Mars, right? There'd be nothing to fight. There'd be no potential disasters to understand and to mitigate against, right? So we're dynamic. Earthlings are dynamic because the Earth is dynamic. As our populations expand, we expand into more and more dangerous places. We have more of us exposed to hazards, including meteorites, I suppose, but certainly dam breaks. And a lot of us in this room, I suspect, are motivated in part to be earth scientists or scientists to try to make the world a more safely designed place. And here's an example of where probably if the geology had been done properly and if the engineering had been done properly, this probably wouldn't have happened. Thanks.